Welcome to our talk at stackconf Online, Challenges in Building a Multi-Cloud Provider Platform with Managed Kubernetes. If you wonder what this is all about, it's basically about building a managed database service across multiple cloud vendors. We have taken on this challenge over the past 1.5 years, and kind of the TLDR is it's still challenging. Kubernetes is a great abstraction, and especially managed Kubernetes solutions such as Amazon EKS or Google Kubernetes Engine, they also remove a lot of the operational effort for a managed database or other service you might want to build. But there are also its challenges because when trying to support different cloud providers, you have to take care of different implementations for security, authentication, authorization, different networking solutions, storage, different Kubernetes versions and upgrade policies in particular, container runtimes and logging. And this is what we'll discuss in this talk. So basically this talk is for you if you're interested in implementing your service either on Kubernetes on top of one of the different Kubernetes managed services by any of your favorite cloud providers, or even if you're trying to implement it across multiple of those cloud vendors. So first of all, the team behind ArangoDB OASIS. So this is the managed database service we'll be talking about here. I just want to give kudos to the team who has actually built this. And so the team lead is Ewout, and I think he and his team, they have done a really great job in building this managed database service. So feel free to also try that out. I'm Jörg. I'm the head of engineering and machine learning over at ArangoDB. And prior to that, I've always been switching back and forth between building infrastructure. So for example, at Mesosphere, working early on Kubernetes as well, and building database services. So right now, I'm pretty happy I can actually combine both those passions. And I even can combine both those passions in this talk because I can talk a little tiny bit about databases, not too much, don't worry, but mostly about infrastructure. So why do you care? ArangoDB is actually a database. So you might wonder, why do they care about talking about setting up a service across different cloud providers? So overall, as mentioned, ArangoDB might be a database. So if you haven't heard of it, it is a native multi-model database. Imagine if a graph database and a document database had a kit together, and so we can basically handle different data models natively, and you don't have to switch between different database products to, for example, combine your graph problem together with like a document data store. It's distributed, which is very important if we're talking about different setup and deployments on Kubernetes, because we actually have to take care of connecting all the different pieces together. It has AQL, a SQL-like query language, and we also support transactions to some degree. So it's open source, so feel free to go and try it out. But I don't want to talk too much about ArangoDB, but why do we care about this container and Kubernetes space? If we are looking at the CNCF landscape, so CNCF is the Cloud Native Foundation, the kind of foundation behind Kubernetes and a lot of the other projects in this space, you can see that the tile for databases is ever growing, and we see like most of our like best known database solutions like MySQL, Postgres. So if you're in the database space, you probably have heard of many of those solutions. Furthermore, we see that for our community, so our open source users, as well as for our customers, containers and Kubernetes is becoming more and more important. So we're seeing a lot of pulls on our Docker images for ArangoDB, but then also even more importantly, we see a lot of pulls for our Kubernetes operator. And in my experience, Kubernetes operators, they really upped the game for deploying stateful services on top of Kubernetes. Originally, it was kind of designed more for like stateless services, but with Kubernetes operator or the operator pattern, we're actually able to run stateful services and also support the complex patterns. So if prior to that there were like those run books on how to update your database, we have a lot of chapters in our documentation and how to maintain upgrade, do failure recovery inside ArangoDB. But this is basically all encoded into the operator. And imagine it's just this kind of like this runbook as code. And so it really makes spinning up a large distributed database cluster much, much easier. And then also maintaining it, updating it, upgrading it, dealing with failovers, and basically all of the stuff you have to do otherwise from a day-to-day basis as a database administrator. ArangoDB OASIS is our managed solution. So if you don't want to set it up yourself, you can basically just go there and with a few clicks have a running instance, a running cluster of ArangoDB here. We have a large number of deployments across different cloud providers. So AWS, Google, and Azure are the currently supported ones, and they are fully managed deployments. So you don't have to worry about anything. You can upgrade with a single click. We do all the maintenance for you in the background. Has inbuilt security, and is also just scalable with a single click of a button. So if, for example, if you look at the UI, you can choose here already the provider, which basically this talk is about. How do we support those different providers? And then you can configure how large should your node be and how much disk you want, and so on and so on. So just a little bit on the OASIS architecture. I don't want to dive into that too much, but it's important to actually understand some of those details to understand how we actually set it up across different cloud providers. So the kind of general architecture is we have a control plane, which is basically the central control plane for all the different clusters which are running out there. So there's monitoring, there's the dashboard, there's alerting, logging. So basically anything we also need to control all the different instances of the ArangoDB clusters running out there. And then there are multiple data clusters. So a data cluster can be, for example, one Kubernetes cluster running in AWS. And one of those data clusters then in turn can hold multiple customer deployments, which basically translates to ArangoDB clusters. So the control plane, as mentioned, it's kind of the brain. It's actually also running on GKE. So there's just one instance for controlling all the different data clusters. And that's currently running in Google, on the Google Managed Kubernetes solution. And this is basically as similar as in the Kubernetes model, kind of this central component managing the creation removal, and it's also kind of the communication hub for like alerting, logging, and other things. The data clusters, they are the actual ones running the different ArangoDB clusters. So we have a large number of data clusters. Imagine, roughly speaking, there's one for each cloud provider, and then for each zone or each availability zone supported in that cloud provider, there's one data cluster. So as we support a large number of different zones across 3 cloud providers, you can already imagine this actually amounts to a large number of data clusters. It's abstracting away the cluster details, and it's also aiming to abstract away the cloud provider details. That basically, for the control component, it's pretty much the same whether it creates a customer deployment on, for example, AWS or on Google, but this is only true mostly. So we'll dive into like the network layers and other details in just a few slides. So, but let's look at what it actually means for us to create a new data cluster. It's actually fully automatic, but in the end, we have different operators for different cloud providers. And they are really different. We choose to implement it using operators. There's actually been that question before. Why didn't we go for something abstract, abstracting away the different cloud provider details? Because we really need that that level of control on the different data clusters. So in the end, it actually means we have an Kubernetes operator. which allows us to create and manage all those different data clusters across different cloud providers. It's designed as like a pull-only setup, and this is kind of for the future what we are currently working on for the next release, to actually also support custom VPCs where you're actually sealed off with your network. So, as that was kind of the overview of ArangoDB and OASIS, let's actually get to the interesting part, and the first step is kind of Kubernetes as an abstraction. So if we think about containers were designed to be an abstraction. And this is not only true for the containers we talk about in software, but also in the earlier containers in kind of the real world, where they really help to kind of standardize. You don't have to worry about what's inside the container. You can put it on a train, you can put it on a ship, you can put it on a truck. And similarly in software, that's kind of the idea. You don't really have to worry about what's inside, but you can just run your container anywhere or almost anywhere where you have a container runtime. But then the next challenge kind of came. Containers, they are great, but we also kind of have to orchestrate them. First of all, for example, a Docker container by itself, if it crashes, if there's some kind of failure, if it runs out of memory, it doesn't restart automatically. So we need something to actually deal with that and schedule them. And with scheduling, also restarting them if there's a failure. Furthermore, we also have to deal with kind of resource management. How do we ensure that actually a container lands on a box with large enough resources, and in our cluster not all containers are started on like a single box and then this box is totally overloaded? And then probably the biggest challenge is how can we actually connect multiple containers to a meaningful microservice architecture. Usually inside one container, we have like a limited business logic, and to really get, first of all, a more complex set of services attached to each other, and then also being able to scale individual components, which probably is one of the big advantages of a microservice architecture. We actually have to do some service management and connecting those pieces together to a larger architecture. So if we want to look at the different abstraction layers, containers are at our first front. Then actually this different container orchestration we talked about, this is actually what Kubernetes is doing for us. So Kubernetes is this really helpful tool which we can deploy across large clusters, and then actually this helps us to manage our containers, to deploy them, to upgrade them. It will automatically restart them if we tell it to do so, and so this is basically our orchestrator. Now this orchestrator can still be deployed. It basically makes it invisible to whatever is deployed underneath. So we can deploy Kubernetes on top of a bare metal cluster. We can deploy it on top of different cloud providers such as AWS, Google, or Azure ourselves. But if we dive a little bit into what it means to actually deploy our own Kubernetes clusters, if we just have a look at the basic components, there's they're usually the master nodes or the control plane, again, to use the same names as we have, or the same same names as we have in the OASIS space. The control plane kind of being the brain of the cluster. This is here with the master nodes where we have the API server, we got scheduler, we got controller managers, and then to persist all the important information, a distributed key value store called etcd. And then we got the worker nodes or the kind of data plane, which is doing the actual works. Here we can see we got the kubelet, kubeproxy, and then different pods running. So pod is basically a combination of multiple containers. So we see this can actually already get pretty complex, especially if we consider a favorite quote from a former colleague of mine that Kubernetes clusters are actually like Pringles. You can't just have one. in typical setups, you actually end up with like a large number of different Kubernetes clusters. At least you're gonna probably have one staging, one for production, and then, as in our case, we actually have multiple clusters for different cloud providers. So in our case, we have like 10 plus different Kubernetes clusters at least, not even counting the different staging environments. So setting that up and controlling all of that becomes already a pretty big nightmare. And this is where kind of the next abstraction layer comes in. And this is actually the cloud providers giving us a managed Kubernetes solution. So Amazon is, for example, giving us the Elastic Kubernetes service. Google is giving us a container engine. And also in Azure, we have the Azure Container Service. So all the big cloud providers, and even if you're on different cloud providers, they probably also have a managed Kubernetes solution by now. And by that, we can actually remove the hassle of having to set up and maintain all those different Kubernetes clusters. All right, so this was kind of the motivation. Why do we actually want a managed Kubernetes solution? Next, why might we want to have a multi-cloud provider solution? So multi-cloud provider solution refers to we're not just picking one of them and implementing our service there, but we actually we choose to implement it across different cloud providers. So from what we heard from our customers and users, often it's actually a company policy. So that can be in or exclusive. So it can, for example, mean we don't want to run on AWS. We don't want to run on Azure for some reason. Often it might, for example, be because it's a competitor. And also an often used argument for multi-cloud provider solutions is to avoid like dependency on a single vendor. So it actually gives customers leverage to switch over from AWS to Google or to Microsoft more easily if they're not dependent on a single managed Kubernetes solution. So overall flexibility, and often I feel it's also, in some cases at least, it's actually a buzzword where it just sounds cool to actually have a multi-cloud provider solution. So before actually going into implementing a multi-cloud provider solution, actually consider the benefits you get out of that. And even though you decide to only implement it on a single service, please remain on this talk, because actually we're talking about a lot of the interesting parts for each and every cloud provider you should care about when implementing even a single cloud provider solution. So what are the challenges we faced over the past 1.5 years? And if we had to group that, it's probably resources and resource management, resource creation, different Kubernetes versions, different security implementations, authentication and authorization, different logging solutions, networking, storage, and then different container runtimes. So if we kind of had to first blow off steam, imagine we had to write an email to each of those product managers running the different managed Kubernetes solutions. Here's kind of the first level critique. But keep in mind that overall we are pretty happy with each and every of these solutions. So on EKS, it's the biggest challenge for us probably is that it creates many resources on the fly, load balancers, security groups, and so on and so on. So this basically each resource, or most of the resources you create, they actually have dependency, and that can make removal pretty challenging because not all resources are assigned tags. So we actually had to create like a pretty elaborate cleanup routine to remove all the components on the fly. Secondly, you can actually feel EKS is one of the older solutions, which on the one hand is good for stability, but on the other hand, sometimes the API also feels a bit old, and we especially felt that around error handling, which is, let's just say, not so structured and involves a lot of string parsing. On GKE, probably the most annoying part. On the other hand, it's probably also pretty good. It's the aggressive update policy. So they actually update to a new Kubernetes version pretty quickly, and then they also drop off old Kubernetes solutions. And if you haven't upgraded yourself from one Kubernetes solution to the next, they will happily do that for you. But if you actually run a managed database service or any service which has like a persistence layer, you probably want to be in control of the update policy yourself. Then on Azure Container Service, we've felt the young age, which on the one hand, again, was pretty refreshing because they have a lot of great ideas around how to structure the API. But on the other hand, currently it's still missing some of the basic features. So for example, VM scale sets, they're quite restrictive. And we actually had to work around the PVC resizing issues, which comes up on one of the next slides in more detail. So let's get started with resource creation, because that's probably the most important part. If you bring up a Kubernetes cluster, you care about the different resources in the background, because that's usually what ends up on the bill in the end as well. So this is what you're paying for. So on EKS, as mentioned on the previous slide, it actually involves a lot of different resources. So VPC, Internet Gateway, Net Gateway, subnets, routing tables, security groups, autoscaling groups. We have a separate AMI, and then the actual AKS cluster. So you can already see there's a lot of stuff happening in the background, and AWS will create many resources on the fly. And then there are also certain dependencies in which you can remove the resources again. So you first have to remove part A, and then you can remove part B, which depends on part A depends on, this way around. And this is especially challenging as not necessarily all resources are tagged. So you kind of have to figure out how the dependencies are. On Google, it's actually much less. So we have a VPC, the GKE clusters, and then the actual node pools. So there we have a lot less number of resources to care about. And similarly on Azure, it's also the resource groups, AKS clusters, the scale sets, and the storage accounts. So that's also pretty manageable. But here we just ran into some limitations. So for example, currently the VM scale sets, they cannot be scaled down to 0, which in some cases this might actually be nice. And then also on the upper side, they're actually limited to 8, which given that we need to create a large number of them, for example, for different groups, this is a pretty tough limit for us. Kubernetes version, and here it's actually mostly Google where we have to deal a little bit with that or manage that a little bit. They're moving really quickly, which on the one hand is great because you always get the newest Kubernetes version, both major and minor versions, but they also actually force those upgrades up on you. They will auto-update your cluster, but as mentioned earlier, you actually, if you have any stateful service, you want to be in control yourself. So you actually have to follow those updates pretty quickly and then upgrade your underlying Kubernetes cluster. Or tell GKE to update your underlying Kubernetes cluster on your own schedule. It's not much work, but basically you should trigger that on your own schedule and not rely on the Google enforced schedule. Kubernetes cluster options. So when setting up your own Kubernetes cluster manually, may it be using Kubernetes the hard way or any of the other solutions out there, it's a lot of work. So this is why we actually choose to have managed Kubernetes clusters. But managed Kubernetes solutions or clusters, they also limit the choices you have. So for example, access to the Kubernetes API server options is something which sometimes is really great. So when bringing it up yourself, you can configure a lot of cool things using the command line. For example, webhooks for AUSI, really easy. But if you have a managed Kubernetes solution on any of the cloud providers, we actually you don't have this option exposed, and this is something we had to work around. Authentication and authorization. Each of those providers actually has its own solution, and typically it's a proprietary solution. There exist a number of different open source and proprietary solutions, but we actually looked at some of them. They seem pretty insecure, and none of those really met our requirements. And again, one of the challenges was that we couldn't configure these servers, the authentication here as mentioned for the API server, simply because we were running on a managed Kubernetes solution. So our current solution is actually to use Kubernetes service accounts and then a pretty light layer on top as the OASIS authentication, relying on those service accounts. So this turned out to be a pretty scalable approach, leveraging basically Kubernetes native tools, aka service accounts, to deploy authentication and authorization across the different cloud providers. Similar problem with logging and audit. Especially Audit Log are really important if you want to follow, if you're dealing with stateful and valuable data, you want to know who had access to it and who accessed it. So again, each cloud provider has its own proprietary solution, and we basically ended up being pretty happy with Grafana Loki coming to the rescue. So we just deployed that, and that's been a pretty common solution across, and pretty scalable solution across all the different providers. Again, for audit logging, we'll discuss some of the challenges when we actually talk about storage. And again, some of the challenges were that we can't control all the Kube API server parameters for logging. So again, a slight drawback of having a managed Kubernetes solution. Storage is actually has kind of two challenges. First of all, it's all slightly implemented differently across different cloud providers. And secondly, probably for kind of like sizing, the biggest challenge is that they all kind of have different performance. Some cloud providers offer options such as configurable IOPS, but overall we had to do a lot of benchmarking to actually achieve different performance classes which are comparable across different cloud providers. And so this is both true for volumes. So the actual volumes where ArangoDB is running on, and then also the kind of cluster external storage, so storage outside of the Kubernetes clusters, for example, used for backup and restore. So if you want to create a backup, you don't want to store that on your Kubernetes cluster, but for example on your S3. And that's actually where we currently need different implementations for the different cloud providers, because that kind of cluster external storage is very different across different providers. Whereas if we are actually dealing with Kubernetes volume, the creation of them is pretty neatly hidden behind the Kubernetes API. But as mentioned, we still had the challenge of different performance characteristics. One of the issues we ran into on Azure is actually that the PVC resizing was broken. So when you kind of resized a persistent volume claim, it changed the metadata and pricing, but we didn't see any changes to the file system. The Azure team, they are really great people there building that, and they helped us with a manual workaround. So we now can deal with that, but it was just a bit confusing at first because it looked changed and then it didn't change in the end. But again, kudos to the Azure team who actually helped us out there, and they are really working on improving the overall structure as well. So that hopefully is fixed soon. So the next biggest challenge, and I would say this is also probably a big challenge whether you go on a single cloud provider or whether you're actually aiming for multiple cloud providers. So our OASIS data clusters, so read this as like the one Kubernetes cluster, it's actually multi-tenants. And so we only get like a single VPC for an entire data cluster. So we still want strong network separations between different tenants for networking and obvious security reasons. So we actually choose here Cilium as kind of the base platform. Of course, this gave us the best guarantees and also the best performance, which is pretty crucial if you're trying to shuffle a lot of data around between different nodes or between different tenants, between different virtual containers in your cluster. That's the right term. So Cilium, what does it promise us? It enables us to specify very simple network policy rules. So for example, pods in namespace A can talk to pods in namespace B, but not pods in namespace C. Rules can be directional. So for example, even though pods in namespace A can talk to pods in namespace B, this is not necessarily vice versa. Those rules are actually low-level implemented using Berkeley package filters, which is a great plus on the performance side. So in short, and you can skip that if you don't care too much about the implementation details, this actually means that all the packages that can remain in the kernel, and so they don't have to be brought out and have a lot of context switching in between. It's supposed to be cloud provider independent, except the installation and setup, which for us is okay because this has to be done once per data cluster, and okay, we can deal with that for each cloud provider. So unfortunately, the reality, it's still great. It's a pretty great tool, and really kudos to the development team behind that. So when it works, it's great. But the cloud provider independence, it's not always the case in reality. So for example, the probably biggest issue we hit was that pod siders are differently set on AWS versus GCP. So for example, on AWS, we had the issue that often the pod siders were clashing for different nodes of your Kubernetes cluster. And that actually means that your Kubernetes cluster doesn't work because you need to have those different networks cider spaces, because otherwise two pods might end up with the same IP address. And so we actually, our workaround for that was pretty simple. If we figure out that we have clashing pod ciders, we're actually just manually draining the node. So just as a result, almost no problem on GCP, so on Google. Overall, I would assume that that's probably the default testing target for Cilium. And in the beginning, we had relative frequent issues on AWS. This actually improved quite a bit with the latest Cilium releases. So from Cilium 1.7 onwards, this got a lot better. And similarly for Azure, it felt in the beginning for all the releases, it was relatively new, but by now we actually also feel much better about that. So as a last item is kind of container runtimes. So container runtime is kind of the piece of software actually running your container, making sure it enforces its memory or CPU limits. And there's actually like a large number out there. So I feel like every year someone is proposing something new, and just kind of as a first very simple structure is actually to structure that in container runtimes and kind of container isolation modules. We could probably have our own talk just about that. But currently we're just relying on kind of the default runtime, which in most cases is going to be container D underneath at least. But I think in the future, we also going to look into especially the secure container runtime. So this is an ongoing project right now, which actually help us to isolate better between different containers. So just recall a container underneath. It's actually just C groups and namespaces. So there's no real performance isolation. It's all still running on the same Linux kernel, and this is where some of those secure container initiatives are coming in, like Kata containers, having an own or lightweight kernel with, for example, Firecracker, Nabla containers, or gvisor, where we actually implemented a part of the Linux kernel in user space, which is a pretty cool project. And this is something where we actually also see that different cloud providers are focusing on different solutions. So for example, Firecracker is heavily backed by AWS, whereas gvisor is mostly a Google product. So what is the conclusion of all of this? So in our experience, if we had to summarize it, AWS is clearly older than, for example, GCP, and for that then also Azure. And this is good on the one hand because it's actually the most stable of them. So we had the least number of network outages. It was a bit slower to bootstrap, and the APIs are showing their age. But overall, we must say like the managed, the experience from the stability point was really the best on AWS. The kind of experience for managed Kubernetes solutions, in our experience, we actually felt that GKE, so the Google Cloud, had a pretty solid and pretty also stable. We had a pretty stable experience, and also the APIs were really well thought out. Again, just from kind of the age. Also the AWS API, it has a lot of features. So for example, provision IOPS, and so also from a performance point, we had a lot of knobs we could use, which was cool on the one hand, but then on the other side, you also have to figure out what to do and what's probably most important for you. So we can say that from an API perspective, it was probably harder to deal with the other ones, but then from a stability point, AWS kind of helped us out. AKS, so the Azure solutions, I would call it kind of the young cool kid on the block. It's less mature if we look at, for example, stability or also the different number of features available, but they have a really dedicated team and coming up with cool features underneath. So we're really curious to see where this is going in the next year. So thanks for listening. I hope that kind of helped you to give an overview of the challenges if you're actually trying to implement your service on top of a managed Kubernetes solution. If you don't want to deal with that, if you just want to try out a database, you can actually get a 14-day free trial for OASIS, or also just try out our Docker containers. So just Docker pull ArangoDB will also get you started on your local box or your favorite cloud provider. Thanks very much for listening.